Alright, in this video we're going to look at the derivative of the inverse tan function, and we'll start the same way. If we have the basic tan function, y equals tan x, the inverse would be x equals tan y, and explicitly written it would be y equals the inverse tangent of x. The inverse tangent of x, the domain, is all real numbers, and the range is negative pi over 2 to pi over 2. So when we're in the same two quadrants as we were with inverse sine. We're going to do this implicitly. To find the derivative, we'll start with x equals the tangent of y. We'll use implicit differentiation, taking the derivative of each side with respect to x. The derivative of x is 1. The derivative of tan y is secant squared y times y prime. Solving for y prime, we get y prime equals secant squared y. Same scenario here. My answer is in terms of not only y but also a trig function of y, and I'd like to get my answer in terms of x. We're going to start off again by saying y is the angle whose tangent is x. And so if y is the angle whose tangent is x, I'm going to set up a triangle with a right triangle. My angle would be, this angle is y. And so the tangent is the opposite over the adjacent. So opposite over adjacent has to be equal to x. So I let the opposite be x, I let the adjacent be 1, and then I solve for the hypotenuse, again using the Pythagorean theorem. We'll call this c. I know x squared plus 1 squared equals c squared. So c would equal, now it would be plus or minus the square root of x squared plus 1. But I know that I am in the first quadrant because of the fact that our inverse tan is only defined in quadrants 1 and 4, and so the secant is positive in the first and fourth quadrant. If you remember the all students take calculus little mnemonic device, all students take calculus. The first quadrant, all trig functions are positive. And in the fourth quadrant, the cosine and its reciprocal are positive. So again, I want to take the positive. So c is equal to the square root of x squared plus 1. So the secant, I want to make a substitution for secant y. The secant of y, since the cosine is the adjacent over the hypotenuse, the secant is the hypotenuse, which is the square root of x squared plus 1 over the adjacent, which is 1, or simply just the square root of x squared plus 1. So when I plug back into the derivative formula, I get 1 over, well, this is a secant squared, so it would be the square root of x squared plus 1 squared, or just 1 over x squared plus 1. So our new formula, d dx of the inverse tangent of x is equal to 1 over x squared plus 1. And the second form of this would be letting u be a function of x, and so the derivative would be 1 over u squared plus 1 times u prime, or again simply just u prime in the numerator over u squared plus 1. This is a reasonable formula to use. So I'd like you to try it. Find the derivative of the inverse tan of e to the 3x. Pause the video and then start the video up again to check your work. So in this problem, u is our e to the 3x. U prime is e to the 3x times 3, or just 3e to the 3x. So when I take the derivative, y prime is going to equal, again, it's 1 over u squared, so e to the 3x squared plus 1 times u prime, and u prime is 3e to the 3x. Again, for those of you who'd rather write it in the other form, the u prime over u squared plus 1, your final answer should be left that way anyway to be simplified. So it's u prime in the numerator over e to the 3x squared. When you raise a power to a power, you multiply the exponent, so that's e to the 6x plus 1, and there's your derivative. Okay, let's look at the last that we have to derive, the secant function, and we'll start the same way. We know that the original function is y equals secant x. The inverse is x equals secant y. The explicit form of the inverse is y equals the inverse secant of x. We're going to take the derivative using implicit differentiation, so we'll work with the x equals secant of y. Okay. Taking the derivative of each side with respect to x, so we get d dx of x equals d dx of the secant of y. The derivative of x is 1. The derivative of secant y is secant y tan y times y prime. Solving for y prime, we get y prime is equal to 1 over the secant y times the tangent of y. We want to do the same exact thing. We want to set up a triangle. We know that y is the angle whose secant is x. We're going to draw our right triangle. Here's our y. Now the secant is 1 over the cosine. The cosine is the adjacent over the hypotenuse, so the secant is the hypotenuse over the adjacent. So I'm going to let the hypotenuse be x. I'm going to let the adjacent be 1. And using the Pythagorean theorem, I'm going to get the square root of x squared minus 1 for the missing side. You can, take a minute and confirm that on your own. I'm not going to take the time on this third example to do the algebra. I think you can figure that out. And so now I need to substitute secant y tan y. So the secant of y is, we know, is x. So substituting in, we get y prime is equal to 1 over, the secant is x. The tangent of y is opposite over adjacent, so that's going to be the square root of x squared minus 1 over 1, or just the square root of x squared minus 1. Now there's one last item. I mean, we set up this model, and what we have to do is we have to make a slight correction here as far as the x. In the formula, the absolute value of x is needed. And I'm really just going to demonstrate that by pulling up the graph. Here is the graph of the inverse secant function. And you'll notice that the slopes are always positive. And so in order to compensate for that, we put in the absolute value of x. Basically, if x is negative, we want to take the opposite of x to get our positive slope. And if x is positive, we want to take just plain old x using that definition of the absolute value of x. So this is the formula. We have d dx of the inverse secant of x is equal to 1 over the absolute value of x times the square root of x squared minus 1. And again, if u is a function of x, then the inverse secant of u is going to be 1 over the absolute value of u times the square root of u squared minus 1 times u prime, or just u prime over the absolute value of u times the square root of u squared plus 1. So as I've mentioned before, you have to do yourself at least the service of memorizing the derivative formulas. There's enough work involved in learning how to